Hello everyone, welcome to the 18th lecture of the Scalable Data Science course on NPTEL. I am Professor Saurangshu Bhattacharya from Computer Science and Engineering Department, IIT Kharagpur. Today's lecture is going to be on Hadoop system. So, it will be the first lecture in a 3-part lecture on the Hadoop system. So, just to recall, in the previous lecture we have seen what is big data and what is the motivation for big data processing. We have seen the issues with big data, what are the issues while you are trying to process big data. Then we have seen the system Hadoop, and we have seen the programming paradigm which is called the MapReduce paradigm, and we have seen a few examples of MapReduce programs, and so we have seen how to express a particular task in the basic MapReduce framework. So, in this lecture we will look at one of the components of Hadoop system, which is the Hadoop distributed file system. Okay. So, first we will discuss what are the motivations behind motivations and characteristics of this Hadoop distributed file system. Then we will see some of the commands that you can use and basically get a feel of how to interact with the Hadoop distributed file system. Then we will get into the system architecture of HDFS, and also we will see a few implementation issues and implementation details of the HDFS. Okay, so, just to recall what is Hadoop. So, Hadoop is a scalable, fault tolerant and distributed system for data storage and processing. So, as discussed earlier, the core Hadoop has 3 very important components. The first is the Hadoop distributed file system component, which is responsible for storing data in a distributed manner and also making this data available. The second component is the Hadoop Yarn component, which is responsible for scheduling jobs in the Hadoop cluster, and also it is responsible for managing the resources of the cluster. And finally, there is the Hadoop MapReduce framework, which we have discussed in the last class. Okay. So, so what is HDFS or Hadoop distributed file system? Okay. So, HDFS is a distributed file system with these characteristics, that it is fault tolerant, scalable and very easy to expand or extremely easy to expand. Okay. And HDFS is used as the primary distributed storage for any Hadoop application. Okay. So, when you are writing an Hadoop application, by default you will be using HDFS as the main distributed storage for these applications. Now, one of the main difference from HDFS to other distributed file systems is that it provides interfaces for applications to move themselves closer to data. As we had discussed earlier, one of the main issues of big data processing is that we waste a lot of time moving data between the different nodes that we are processing it in. So, paradigm or idea is to, instead of moving the data to where the computation is going on, you can move the computation closer to data, and we will see how Hadoop distributed file system helps in that. Then Hadoop distributed file system is designed to just work, that is, you need not know the internal functioning or how exactly it is designed, but if you know the design and internal functioning, then you can better utilize the Hadoop distributed file system, and also you can better debug the programs that use Hadoop distributed file system. So, what are the design assumptions behind the Hadoop distributed file system? So, the first design assumption is that hardware failure is a norm. So, basically all the data that you store in Hadoop distributed file system has to be tolerant to hardware failure, that is, at any point in time a particular disk that you write the data in may fail, and hence it should have a backup of that data. So, this is the first assumption. The second design assumption is streaming data access. So, data will be accessed in a streaming manner, one after the other, one record after the other. So, this is true for also other standard file systems, but this is especially true for HDFS, since the speed of reading the data is of essence here. So, this is one of the assumptions. The other assumption is that is the write once and read many times assumption. So, here the main idea is that since you are writing such big data files, it is expected that you will write this big data once and then use it many times. Otherwise, you have not really taken a lot of advantage of this big data, because you have spent so much effort gathering and then writing this big data. It is expected that once you write this, you will read it many times and use it many times. The next assumption is that it is a high throughput, not low latency system. So, what this means is that if you try to access randomly data, or if your application is designed in such a manner that you are making many random accesses to different files or even different parts of the same file, then your application may run slower, as opposed to if you make a high throughput read of the whole data, okay, and then it is designed for large data set, which is obviously the case. Okay. Keeping these design assumptions in mind, HDFS performs best with a modest number of large files. Okay. It is optimized for streaming reads, as we discussed, and another important characteristic of HDFS is that it does not try to implement the low level file system, but it is a layer on top of the existing file system which is provided by the operating system. Okay. So, what are the details? So, the first thing is that, like any other file system, even in Hadoop distributed file system, the data is organized into files and directories, and just as you work with any Unix distributed files, you can also work with files and directories in the Hadoop distributed file systems. Now also similar to standard file systems, files are divided into blocks, but now unlike standard file systems, these blocks are distributed to different nodes in a Hadoop cluster. Okay. So, these blocks are data that is sitting on the native file system of different nodes of the Hadoop cluster. Okay. At the time of reading, the block placement is known, which means that you know the node on which a particular block is placed, and hence you can you can schedule your jobs or your MapReduce tasks in such a manner that the computation goes to the data, that is your application or the client that is reading the data is close to the node where the data is being read. Now, an important concept in Hadoop distributed file system is the replication concept. Okay. So, every block every block is replicated a certain number of times. Okay. Now, this replication is useful for first of all speed of computation, because for example, if a particular block is placed is replicated across 3 different servers, we can schedule the computation close to one of those servers, and then the chance of finding a free, let us say, compute slot in one of the 3 servers is higher than if the data was not replicated. It was only on one server, then the chance of finding a free compute slot is lower. The second important gain of replication is the fault tolerance, that is, if one of the server goes down, then you can run the job on the other server without losing the whole job. Okay. And the third is, it can be used for self healing, that is, once a particular node goes down, okay, so then since the data is already replicated on other nodes, those nodes can again heal the file system, in the sense that they can replicate the data onto a 4th node, and hence even though one node is down, the total number of replicated factors is still 3. Okay. So, there are 2 main components of the HDFS file system. Okay. So, the first component, and these are these are software components which are running on the servers. Okay. So, the first software component is the name node component. So, this is the heart of an HDFS file system. It maintains and manages all the file system metadata. So, we will look at what metadata it manages, but mainly, for example, for a given file, it stores which blocks constitute these files and on which nodes these blocks are stored, etc., etc. Okay. The second important component is the data node component. Okay. So, this is where HDFS stores the actual data, and almost you can think that any Hadoop cluster, almost all the nodes will work as a data node, whereas there will be one or 2 name nodes. Typically, there will be only one primary name node and then maybe a few secondary name nodes, which become useful when if the primary name node goes down. So, this is an example of HDFS architecture. You can see that. So, as you can see, so this is an example of a HDFS URL. So, /user/p-co-thuri/data, and then there will be part files. So, /user/p-co-thuri/data is the location, and then under this location there are these part files which are stored. So, this is a very typical structure of a HDFS file system. So, there is the first 3 are the directories. So, there is the user directory, under which there is this directory, and under which there is this directory, and so on and so forth. So, as you can see, the components here are, so there is the name node which is storing all this metadata. So, it is storing the file name and it is storing the block IDs, etc. Now, this is the most important thing. It is called the HDFS client. So, the HDFS client is the software that is programmed by you. So, for example, HDFS client could run inside a mapper job that you as a programmer have defined, or it could also one could also use inside a normal program, not a MapReduce program per se, but inside a normal program an HDFS client. Okay. Now, the HDFS client should typically interact first with the name node to get the details of the data node where the data is stored or where the blocks is stored, and then it would also interact with these data nodes to directly get the data. Okay. So, and these data nodes are, as you can see here, running on almost all the machines in the Hadoop cluster, which are connected to their local disks, and these are stores for the block, and the data nodes and the name node, they interact with each other to provide various functionalities like replication, balancing, heartbeat, etc. So, they basically perform all the function. Okay, so this is just a view of few of the commands that you can use in HDFS. So, for example, you could use the list command just as in as a Unix command. So, you can write HDFS space DFS minus LS, and this would list the contents of a current directory. So, whenever you are logged into a Hadoop cluster as a Hadoop user, you will have a current directory. So, Hadoop will maintain a current directory, and then you can use this command to view the contents. Similarly, you can use other commands to view, for example, contents of root directory, the second command, or recursively view the contents of a particular directory. Now, similarly, so you can use the du command to view the disk space occupied by various directories. So, for example, if you give a subdirectory, you could get that it would list all the sub files in this directory, and then it would list the space occupied by those files or directories in this directory, or it could give you just a summary if you use the -s flag, and it could give in a human readable format also with just the -h flag. So, commands are pretty much similar to a Unix command. So, you can use it as if you are using a Unix file system. Similarly, you can use, for example, -mkdir, which is similar to the make directory or mkdir command in Unix, and then so one of the important tasks is to copy data from the local disk. So, you are logged into a Hadoop server with an account to one of the machines, okay, and in the local file system of this machine, since you have an account, you may have some data. So, let us say this data is called this tutorials data geneva.csv, then you can use the copy from local command, okay, and you can give the name of the directory in which you want to copy. So, this directory should exist. So, you have already created this directory, and now you can copy the data there. And similarly, once you are done with all the processing, you may want to copy the data from the distributed file system back to the local file system, and for this you can use this copy to local command. Okay. Similarly, you can get so access controls. So, just like a Unix file system, the Hadoop file system also supports access control, which is the owner of a file, and then what permissions do the owner has, what permissions do the group has, and what permissions do other has. So, it has exactly the same access control model as the Unix. Similarly, you can get some statistics, like for a particular file you can get what is the replication factor, what is the creation time, modification time, last access time, and so on, using this -stat command. So, again these are very useful commands. And finally, there are two commands, one is this -put and the other one is -cat. These commands are useful for streaming data. So, -put allows you to stream data from the std in directly to a distributed file system without writing it to a local file system. So, this is very important because many times you have a very big data which is generated from some other application. Maybe you are having you have the data in a zipped format or some such format, and you want to directly put it to HDFS without putting it to the local file system, because your local file system does not have enough space. Then you can use these kind of commands. And cat is the opposite of that. Cat will allow you to print or will allow you to show a file in a Hadoop distributed file system onto the std out, okay, or onto your screen. Okay. So, just to recall, as we have discussed, the goals of HDFS are, so in order to store very large distributed file, something like let us say 10,000 nodes, 100 million files and 10 petabytes of data. So, these kind of statistics you need, so it is not useful to use HDFS for storing a very small amount of data. Okay. Moreover, it assumes that you are running this whole Hadoop system on commodity hardware. So, hardware failure is the norm, and hence files have to be replicated, and the file system is designed in such a manner that it detects failures and recovers from them. Okay. Also, it is optimized for batch processing, that is okay. So, the data locations are exposed so that computation can move to where the data resides, and when that happens, it provides a very high aggregate bandwidth. So, basically what this means is that when you start a computation, your results may start coming slower. So, it is not a low latency data processing, but it is a high throughput, that is a large amount of data will be processed in a short amount of time. And another design which is also common to Hadoop is that it runs in user space and on heterogeneous operating systems. So, you are not really bound to the system which on which the whole HDFS system is running. And as we have discussed, so you have only single namespace for the entire cluster. So, everything is under the root directory, which is / and you have different subdirectories models, just like Unix file system. And we have also seen that you have write once and read many times access model. Now, the way this works is that so mostly you can read, you can do a contiguous read very fast, You can also do a seeking read, which is slightly slower, and you cannot modify an existing file, you can only append to existing files. We will see why this is the case with the architecture. Okay. So, files are typically broken up into blocks of big size. So, typically 128 MB is the block size, which is much higher than the standard block size for file systems, and each block is replicated on multiple data nodes. Now, your HDFS client is directly interacts with the data nodes to access the data. So, this helps in avoiding the bottleneck at the name node level, where only the metadata is stored. So, the metadata is typically much smaller than your entire data. So, so that there is no single bottleneck, the client has to be intelligent enough to read the locations of the files from the name node and then directly interact with the data node in order to access those data. Okay. So, so as discussed already, metadata for the so the name node stores all the metadata. So, typically it will store a list of files, okay, and then it will store for each file a list of blocks, okay, and then it will also store for each block the list of data nodes on which these blocks are stored. So, this is the hierarchy in which it will store attributes. Moreover, for each file it will store attributes such as creation time, replication factor, etc. Okay. Now, this entire metadata will be stored in the memory for the name node. So, typically the server which will host name node is expected to have a high memory, okay, and this is accessed by all the applications in the entire cluster. Okay. And the data node acts as a block server. So, typically a data node would not only store the blocks in its local file system, okay, but it will also act as a node for processing data in the MapReduce framework. So, that you can have data local computation. So, so it will store the block data in the local file system, and then it will store some metadata for the block like the checksum and etc. And then as a general rule it serves the data to the and the metadata to the clients which connect to them, and it will also periodically interact with the name node to send the block report to the name node. And the third functionality of the data node is that it facilitates pipelining, which we will see in a minute. Okay. So, this architecture we have already seen. So, just to make the point here that so whenever a client accesses whenever the client accesses a name node and gets the name node gets the metadata for a particular file like home, food data, and then let us say it is there on the third server, then it will access that particular data node directly and gets the data. Okay. Now, we discuss how does a HDFS read client function. So, a HDFS read client first gets so it has to read a particular file. So, it first calls the open function, okay, which accesses the distributed file system, and then it accesses the name node, and it basically results in getting the block locations for this particular file. So, and this block location is now transferred to this HDFS client, which creates this FS input data stream object, where all these block locations are stored, and this object now initiates the reads from this block. So, this object will initiate the reads one by one from the different data nodes, and the data nodes will directly supply the data to the read to the client in this machine. And then once it is done with reading all the blocks, it will just issue a close message, which will result in the completion of the read activity. Now, this is simple. On the other hand, the write operation is slightly more complicated. The reason the write operation is more complicated is because when you first when you write a new file, so you can either append to an existing file or you can write to a new file. So, you call the create function to the name node. The create function then creates some blocks on some data nodes and returns the list of blocks to the FS data output stream object, which is created on the client side. Then the client writes directly to the data node. So, this gives the data nodes, this gives the address of the data node to which actually three data nodes. So, whatever is the replication factor, that many data nodes to the client. So, the client issues a write request to the first data node that it receives, and then that particular data node actually takes care. So, the data nodes, they among themselves take care of the replication. Okay. So, for example, the first data nodes now issues a write to the second data node. So, the client writes to the first data node, the first data node writes to the second data node, and the second data node writes to the third data node, if the replication factor is 3. And then the acknowledgement comes back from the third to the second and second to the first, which is finally transferred back to the client. At that point in time, this particular write request is complete. So, you see a particular write request takes a lot of time to execute. So, what the file system does or what the write client does rather is it breaks down the data into different blocks, and then it issues the write request to the blocks in parallel, and then the data comes back, and once all the write requests are complete, the client can issue a close request on the file, and then the whole write operation is complete. Now, here one important question is how to place the blocks. Okay. So, multiple strategies can be used. So, practitioners by trial and error arrived at the following strategy. So, wherever the data node client is, the first write or the first replica happens on a local node if it is possible. Okay. So, the first replica of a block is written onto a local node if possible. The second replica is happens on a remote rack. Okay. So, typically, as we have discussed, the servers are arranged in racks. So, the second replica happens on a rack different from the node of the first rack, okay. And the third replica happens on the same rack as the second replica. So, this is because then there is a rack local write from second to third, but also it ensures that that in case of failure of an entire rack, you have the data on at least 2 racks. Okay. So, this is the write placement. This is the strategy when you write data onto a HDFS rack. When you read data, your read is typically from the nearest. So, if it tries to do a rack local read, and if not possible, it tries to read from the nearest rack. Okay. So, the single point of failure for the HDFS file system is the name node. Okay. So, if the name node fails, then so if any of the data node fails, then so the whole file system or the whole HDFS file system is immune to that, because there are many data nodes which are there, and any particular block is actually written onto something like 3 data nodes or whatever is the replication factor for that HDFS. Typically the replication factor is 3. So, it is unless all 3 data nodes on which a particular block is existing fail at the same time, which is highly unlikely, one can always access a block. But if the name node fails, then it is a single point of failure. So, the only way at that point in time is to actually switch to a secondary name node. Yeah. So okay, and we have already discussed data pipelining. Okay. So, to conclude, today we have discussed the structure of HDFS, and we have discussed the shell commands, and we have also discussed the architecture of how the file system, what are the components and how each of the components interact with each other at the time of read and write, and we have also discussed some of the internal algorithms like the write pipelining algorithm. So, the references for this is Hadoop, the definitive guide for by Tom White, and also the mining of massive data sets by Jure Leskovic. Thank you.